Hello everyone. In the last lecture we started discussing the concept of equivalency. If you remember, we said if you have two boxes and we claim that these two boxes are equivalent to each other, what it means in electrical domain is that they behave the same. One of the ways that we can test the behavior of the system is to connect it to a signal and look at how it responds to that signal, and if the response is the same, then the two are behaving the same electrically speaking. So one of the kinds of signals that we can try here is a voltage source. So we connect it to a voltage source and then look at the current that is going into it, and if we connect both of these boxes to the same voltage source and look at the current, and if the two currents are equal to each other, then we say these two are equivalent to each other. Now, a result of Vs divided by I1 and Vs divided by I2, by definition, is the resistance of that box, right? That's just how we define resistance. We take the voltage across the device, the system, or a component, and we say resistance of the box is equal to the voltage across that component connected by the current that is passing through it. So that's for box 1, and for box 2 we define the same thing, Vs divided by I2. If I1 and I2 are equal to each other, then our box 1 is equal to our box 2. In other words, whatever the resistance is inside, or whatever component sits inside, I can turn the behavior, or also, in other words, symbolize or model the behavior of the box with just single resistance, which is equal to the voltage that is passing, is the voltage that is applied to it divided by the current that is passing through it. And that's a very powerful technique that we are going to use from now on, and it's used all the time when you're dealing with complicated network of components connected to each other. You can always remodel them as just a few components, and later on we're going to learn how to do modeling of circuits when we start talking about Thevenin models and Norton models. But one component of that model would be the equivalent resistance of the model, which is simply if you connect a voltage source and that's the only source that you connect to the circuit, and look at the current that is passing through it, then divide the voltage by the current. That would give you the equivalent resistance of the system. So we tried that with a series of 3 resistors connected to each other, and we said the equivalent resistance is just each resistance value added to the next, and we said you can extend that to any number of resistors as long as the current that is passing through all the resistors is the same. In other words, if they're in series, just add values of the resistors to each other, and we proved that. The way that we proved it, we basically did circuit analysis. That's how you do everything in electrical circuits. Now, we're going to try that with a different kind of resistor connection. Now, this specific type of connection is called parallel connection. So in the way that I have drawn this, R1 and R2 appear to be also parallel geometrically to each other, but that really doesn't matter. To tell you the truth, I'm going to actually avoid that and make them not in parallel geometrically to each other, so that you get used to this and it wouldn't confuse you later on. So what does a parallel connection mean? So if you notice, the node across R2 and the nodes across R1 are actually the same. So these two, because they are connected through resistance, zero resistance wires. So when I want to identify nodes, there's the same node on top of R1, R2, and the same node at the bottom of R1, R2. And that's basically when you can call components in parallel parallel to each other. If they share the same node on both of their terminals, then those components are in parallel to each other. Now, regardless of whether or not, geometrically speaking, they're in parallel to each other. Okay, so let's do circuit analysis for this circuit and calculate the equivalent resistance for it. In other words, let's connect this to a source. Look at the current that is passing through. I'm going to call that IS. Divide the two by each other and see what would be the equivalent resistance. And then again, why are we doing that? Because if I do exactly the same for the box that is down here, we know that Vs divided by Is in this circuit would be R equivalents, right? So what if these two are behaving the same? The result of Vs divided by Is for this circuit has to be the same as this one. So whatever we end up calculating is equal to equivalent resistance. So let's start. Let's identify the nodes. So we have, in this circuit, we have one node down here, right? One node up there and another node here, which is basically actually the same node. So there's one single node for this whole thing. So we have really two nodes. That's all we have. Currents, Is there. I'm going to call this one I1, then call this one I2. Is, I1, I2, and then now I'm going to take this as my ground, and when I want to label this one, I'm going to avoid calling that a different variable and just call it Vs. Why am I doing that? Because I run the equation for this component in my head, and I know that the voltage or the potential of the top terminal is equal to the potential of the bottom terminal plus the potential difference, which means that up there is 0 plus Vs. Okay, so with that in mind, I'm going to move on to the next step, which is writing KCL. So I have two nodes. I have to write KCL for. I can write KCL for two nodes, but I don't have to write it for that one. For this one, and by the way, let's be consistent. Move Is where it belongs on the component. Okay, so Is goes into that node, and I1 and I2 are leaving that node. I'm going to add them up. So Is has to be equal to I1 plus I2. I can write the KCL for that node. It would end up being the same, so I'm going to skip that. And then write equations for the components. I have three components. I already wrote the equation for that component, so there's only two that are left. For R1, I know I1 is equal to Vs, the potential on top or on one side, minus potential on the other side, divided by R1, or blah, for R1. Then I2 is equal to Vs minus 0 divided by R2, and we're done. So the next step just is math. So I take these two current values and then put them in that equation, the KCL equation. So Is is equal to Vs divided by R1 plus Vs divided by R2. So what I was looking for was Vs divided by Is, right? At this point, I have actually calculated what Vis is, if I knew what Vs is, right? But what I really care about at this point is Vs divided by Is, because that would be the equivalent resistance to both those two, and ends up being R1, R2 divided by R1 plus R2, which you can actually rewrite the same thing as 1 over R1 plus 1 over R2 inversed. Most likely you remember this equation, and this is the equivalent resistance to these two resistors in parallel to each other. You have most likely seen this in other courses that you have taken, but if you didn't know how to prove this equation, there you go. You just do circuit analysis using the same algorithm, and you end up getting this. Now, again, you can actually take this approach, take this problem, and extend it to any number of resistors being in parallel to each other. So, for example, if instead of just 2 resistors, I was dealing with 3 resistors in parallel to each other, it would be 1 over R1 plus 1 over R2 plus 1 over R3, and the whole thing inversed, and that would be the equivalent resistance. Right? So, generally speaking, I can say 1 over R equivalent of n resistors in parallel to each other would be equal to 1 over R1 plus 1 over R2 all the way to 1 over Rn. And you can prove that by just doing exactly the same thing. This is actually one of the problem statements in the book, and I may assign it as a homework, but it's really simple to prove. Basically follow the same algorithm, just the number of equations that you would be dealing with at that point would be like you would have 1 KCL, but then the number of equations for components would be n, and you just follow exactly the same routine, and you can prove that equation up there. So with this, now we know how to calculate the equivalent resistance when the resistors are in parallel to each other. We already know how to calculate the equivalent resistance when the resistors are in series to each other, and we can use this knowledge to now start approaching relatively complicated combination of our network of resistors connected to each other and calculate equivalency for those circuits using these 2 techniques that we just learned about: equivalence of resistors in series and equivalent of resistors in parallel. In the next lecture, I'm going to start doing more of that and see how we can simplify resistive circuits using the knowledge of these 2 shortcuts that we learned. Thank you very much.